Hello, everybody. Welcome back. Today we're going to be looking at Unit 7.10, which is all about the reaction quotient and Le Chatelier's principle. If you're following the order of my videos, I'm going a little bit out of order with how College Board does it, but to me it makes a little more sense to talk about this concept I'm going to talk about today before we get into some of the heavy calculations involved with equilibrium. So let's get started. So if you'll recall, this reaction quotient Q is calculated the exact same way as K, the equilibrium constant, the only difference being the equilibrium the molarities or the partial pressures involved in that expression are conditions not at equilibrium. But when I say calculated the same way, I mean it's products divided by reactants. It's just that the numbers we would plug in would be numbers not at equilibrium. Now, the title of this subunit involves Le Chatelier, and Le Chatelier's principle is something we're going to talk about in a little bit more detail later on in this unit. But to just kind of give you a summary, if you have a situation, a reaction that is at equilibrium, and you do something to mess that up, okay, maybe you add more of one of the parts of the reaction, or you change the pressure, or you change the temperature in the room. You do something to disturb the system. Well, then it will no longer be at equilibrium. And so we could calculate a value for Q, because if you disturb the system, then it's not at equilibrium. It's not at equilibrium anymore. And what we're going to look at today is, okay, so you've disturbed the system will always get itself back to equilibrium. That is to say, equilibrium will always be restored. And that's what Le Chatelier's principle essentially says. If you disturb the system, it will do what it needs to do to relieve that stress, and equilibrium will be restored. Okay, the reaction will shift in one way, either in the forward direction or the reverse direction, to bring Q back into agreement with K. Of course, remember, and we'll talk about this more later in detail, remember that only changing the temperature that's the only disturbance that can actually change the value of the equilibrium constant. Okay, so as I said, and if you'll recall, if Q is equal to K, then we know that this system is at equilibrium. But what we're going to see today is a situation where they're not equal. Okay, so let's say you are given information. You're given either molarities or partial pressures, and you use those values to calculate Q. And you compare it to the equilibrium constant value, and you see that Q is less than K. Okay, well guys, this is how I want you to, let me change color here. This is how I want you to think about it. Both Q and K are calculated in the same manner. Molarity of products over molarity of the reactants. If Q is less than K, I want you to think about this fraction here, products over reactants. If Q is less than K, that's like saying that fraction is too small. Q is less than it needs to be. So I'm going to rewrite this fraction in an exaggerated way. Imagine this as like very small amount of product over a very large amount of reactant. Okay, so think about it. If you had a fraction like that, with a small value for molarity of products divided by a very large value of reactant. That would give us a pretty small value for Q. One way to think of that is, this situation, we don't have enough products. We need to make more product and use up some of that reactant so that the numerator becomes larger and the denominator becomes smaller. So what happens? The reaction will shift in the direction that's going to consume reactants. The slide says consumer. We're going to shift in the direction that's going to consume reactants and produce more products. So it's going to shift in the forward direction. Okay, that is what's going to happen so that Q becomes aligned with K. To get Q back to equaling K, this reaction is going to shift towards the product side. Ladies and gentlemen, please do not say on a test or an AP exam, the reaction will shift right. It's kind of an old way to say what's happening here. You need to be more descriptive and say this reaction will shift to consume reactants and produce more products. Okay, please don't say shift right. Okay, what about the other situation? If Q is greater than K, well, here's how I want you to think about that situation. And I'm going to do an extreme. That would be like large amount of product over very little reactant. Okay, and that's like a problem. We have too many products. Okay, we need to use up some of the products and make some more reactants. We need to make the numerator smaller and the denominator bigger. How will we do that? By shifting in the direction that's going to consume some of those products and produce more reactants. Please don't say shift left, okay? You have to be more descriptive than that. Shift to consume products and produce more reactants or create more reactants. Okay. So let's look at a sample question. And you can read it for yourself. If you want to pause the video, you can. Okay. We're given a balanced equation. We're given the value for the equilibrium constant. Okay. It says in an experiment, 0.00050 molar nitrogen monoxide, 0.155 molar chlorine, and 0.050 molar NaOCl are found at equilibrium. Okay, stop there. That means those molarities are at equilibrium. Okay? The next part says if the volume is cut in half, determine the value of Q. That's the first part. Solve for a value for Q and the direction the reaction will proceed to reestablish equilibrium, because that's what Le Chatelier's principle tells us. If we disturb the reaction, disturb the equilibrium, equilibrium will always be reestablished. It's our job to determine what direction that will be. Okay, so pause the video, see if you can do this. All right, let's see how you did. Now, remember, of course, that to calculate Q is the same expression, the same products over reactants as K would be, okay? But if we cut the volume in half, okay, we reduce the size of this container somehow, that is going to double all of those molarities. They are going to become twice as concentrated as they were before. So let's look at it. So first of all, I've written my Q expression, which looks exactly like a K expression would. And then I have plugged in molarity values of each piece of this reaction, but I have doubled them from where they were before. Okay, if you cut the volume in half, then the molarity is doubled. So I doubled all of the molarities, and this is what I get for Q. When you compare that to the value for K that we were given, which I believe was 1.55 times 10 to the negative fifth, I can see that Q is greater, which means, remember, this is how you want to think of it. It's like you have too much product. So how is equilibrium going to be reestablished? We're going to shift in the reverse direction to consume some of those products and create more reactant. That's how you want to say it. Don't say shift left. Okay? You will not receive credit for that on the AP exam. Okay? So that's just a sample question, on what it looks like if you have to actually calculate Q and make a decision as to what's going to happen to the equilibrium, or what's going to happen to reestablish equilibrium. So I hope that you have learned a little something today. We're going to take some of these skills that you just learned today, and we're going to apply them with some of the heavy-duty math in the next subunit. So I look forward to seeing you next time.